resist that. I would very much like to talk about problem 29 in lecture, but I really shouldn't. It's hard for me not to talk about it even now, but you should use the summation notation for it. All right, so like, are we talking about the trace part, AB? It's like the trace of AB. You want to write that literally as the sum I equals 1 to n of AB II, right? But what is AB II? Well, AB II is itself the sum k equals 1 to m, or whatever it is, of a sub I k, b sub k I. But then you're looking at a double sum of a product of two numbers which commute, and then you can just flip the sums and rewrite it in the other order. Do not try to do it with like plus dot dot notation. It will not go for you. I've seen students try it before. I don't think I've seen more than one conquer it in the expanded not using index notation way of things. So if you're trying to look at it in terms of like an explicit big box of numbers, it won't go well for you. I will, I think I hit record. So somebody's asking me about 29, if you guys are wondering. Let me begin with a scripture. It's one I learned when I was little. There's Romans 3:23. It says, for all have sinned and fall short of the glory of God. And I think that's helpful. Remember, we're all in the same boat, right, before Christ. And it's just sobering. But anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for this class. Just ask you to help us to understand the theory of inverse matrices better today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me just get straight into it here. So, in this, so I gave at least one of you who's not here advice about how to solve one of the problems in the homework, and I was like, well, you had looked up on YouTube how to do something. That's always dangerous in here, to go to YouTube and try to find out how to do problems, because YouTube doesn't know where we are. YouTube doesn't know what we know. YouTube can tell you to use things that you're not allowed to use. This course has a linear progression, funny, of ideas which I intend for you to follow. And if you jump ahead and use forbidden fruit, so to speak, then you're not learning what I want you to learn from that homework problem. I know what you know in terms of the discussion of this class. I want you to attack the homework problems on the basis of that discussion, all right? So if you go to YouTube, they don't know that, and they'll tell you things you're not supposed to know yet. So then you won't learn what you're supposed to learn from that homework problem, and it'll put you at a disadvantage. But anyway, long story short, I have this one problem where I say solve ax equals to I in the homework, right? And I told one of you, like, multiply that out. You get 4 equations in x, y, z, w. One of them's equal to 1, one of them's equal to 0, one of them's equal to 0, the other one's equal to 1. It's just a matrix equation. 2 by 2 matrix equation gives you 4 equations. Those are 4 linear equations and 4 unknowns. You know how to solve it, right? And that would be a fine, if you already did that problem, that's how you should have done it on the basis of everything we talked about before today. But after today, there will be another way to solve that, which is a little bit easier, all right? So, but I had in my mind that your homework was due today, which I've been giving some advice on people who've come to talk to me about homework on the basis of that. I forgot my own. I gave you guys till Friday, so sorry about that. Anyway, getting to the point here, we want to talk about invertible matrices. And so, to understand invertible matrices, we have various goals. We'd like to understand their properties. We'd like to understand which matrices you can invert, which you can't. And that's pretty much what we're after today. And of course, we also want to understand the connection to the original question that we posed in this course, which is, how do you solve a system of linear equations, right? Because these do give you an answer to that, in part. Although it's a limited, oh, I'm sorry. I shouldn't deny you guys what you love. There, you feel? There. I'm sorry, I almost forgot. My apologies. All right, so here it is. I'd made this definition another day, but here it is. If A is a square matrix, right, an n by n matrix, and there exists B, another square matrix, right, such that AB is equal to I, which is also equal to BA, then A inverse is equal to B. All right. We do not write ever in here 1 over A. This is not something people talk about, right? So because we don't want to confuse people and make them think that it's actually division by a number, it's not. This is the multiplicative integral. Now you might say, well, that's kind of dumb. You could write 1 over A and you wouldn't get into trouble. Well, maybe, maybe not. But the key is with matrix multiplication is it doesn't commute, right? So when you write 1 over A, it tempts you to do other things based on arithmetic, which assumes commuting. And so it's just a better practice to the inverse of the matrix. We denote it by A inverse, the multiplicative inverse of the matrix. All right. So the question is, we have a number of questions, right? One question would be, if this inverse exists, what are its properties? And then, of course, the other question is, how do you actually calculate it? Right. So I'm going to show you a series of theorems which will answer these questions. Our first theorem, we've done half of this already, but we'll do it, the rest of it today. And the theorem is this. AX is equal to 0 if and only if, excuse me, my bad. AX equals to 0 only for x equals to 0 if and only if A inverse exists. If you don't quite know what I'm saying and you want to put it in your own words, what I'm saying is that the only solution to the AX equal to 0 is the 0 solution. All right, that's what I'm trying to say. All right, this is a biconditional. One of the conditions is super easy. So like the converse direction is super easy. Here's how that goes. A inverse exists, then AX equals to 0 implies A inverse AX equals to A inverse times 0, which implies that the identity times x is equal to 0, which implies that x is equal to 0. So there you go. The only solution to the homogeneous equation is the 0 solution. If the inverse exists, that is a necessary consequence. All right? By the way, we have an immediate corollary to this, right? This, what I just wrote in blue, we can immediately extract from that a corollary. What's a corollary? It's a related fact which is like immediately true, right? Theorem is theorem is essentially a fancy way of saying, hey, look at this, this is interesting. Corollary is actually some old word that has to do with like a flower. So it's like a flower that's grown from the theorem, something like that. Anyway, so corollary, if AX equals to 0 for x not equals to 0 for some x not equal to 0, then A inverse does not exist. Right? That's a logical consequence of what I just worked out in blue here. Because that would mean that there's more than just 0 as the solution, right? Which would contradict this calculation. So if you want to check if a matrix is invertible or not, study the homogeneous equation, find out if it has non-trivial solutions. If it does, game over, the matrix is not invertible. All right, so then what? Now the converse to this is, the forward direction for this proof is not as easy. All right, so this way. So suppose that AX equals to 0 implies x equals to 0 only. I guess you could say it this way, AX equal to 0 if and only if x equal to 0, all right? So what does that mean? This means if we look at the reduced row echelon form of A concatenated with 0, what do we get? It has to be what? It has to be the identity matrix and 0, right? Because this system of equations has that as its augmented coefficient matrix, and this system of equations has that as its augmented coefficient matrix, right? Two equations are the same if they have the same solution set. As we've learned, that means that they're row equivalent, right? Do you guys understand what I'm saying? Does this make sense to you? So if 0 is the only solution, that means when we do the row reduction, we must have pivot columns. The first n columns have to be pivots, right? And the last is the solution, which is 0. I hope you've done enough problems that that's kind of like, oh, OK. Right? All right, so how does that help us prove A inverse exists? OK, so this also tells us what? The reduced echelon form of A is actually equal to the identity matrix, right? Right? Stripping off the last column. But we learned about elementary matrix, the identity matrix. We learned about elementary matrix, right? There's a finite sequence of elementary matrices we can multiply by A to get the ref, right? So this is equal to what? Like EK, let me just do dot, dot, dot here. Dot, 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 E2 times E1, right? So these are the elementary matrices necessary for the row reduction that accomplish this reduction, right? That times A gives us I. What does that mean? Oh, so you're like, put us out of our misery, just call that E. I like that. So EA. Cool. Well, that's half of what I need, right? That's half of what I need, because for A to be invertible, I need another matrix, right, such that BA is equal to I. That's the pattern, right? So what are we going to claim? See that, guys? So this, and let's say, this, put it to I like that. So this suggests that B we should set equal to E. All right? So that's half the battle. Right? What else do I need to show? I also should show that what? AE is equal to I. Right? So the question is, why is that true? So what I do is in the notes, let's see here. Oh, okay. So to prove this, I do something a little bit circuitous, which is I solve this other equation for A. How do I solve that equation for A? So in order to show this, I actually solve that for A. Let me show you how that's done. So the thing is, every one of these elementary matrices is itself invertible. We talked about this the other day, right? To do the inverse of an elementary matrix, you just undo the row operation and look at that elementary matrix, right? So like every row swap elementary matrix is its own inverse. If one elementary matrix is like row 1 minus 2 times row 2, then the inverse is going to be like row 1 plus 2 times row 2, something like that, right? Anyway, the point is every elementary matrix has an inverse, which is also an elementary matrix. So if you take this equation right here and we solve for A, what do we get? So we can solve this equation for A by multiply by like EK inverse, then EK minus 1 inverse, and so forth and so on, until I finally multiply by E inverse, then E1 inverse. All right, so if I multiply this, and I'm talking about multiplying that equation on the left. See that? So let me write it out in gory detail. So E1 inverse, E2 inverse, dot, 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 dot. Eventually we get to EK inverse. All right, multiplying that times this EK, dot, 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 dot. E2, E1A is equal to the product of the inverse elementary matrices, E1, EK inverse, times what? Times the identity matrix, right? So I'm just taking this equation right here and I'm multiplying by the product of those inverse elementary matrices, all of which exist. All right? But what happens to the product over here? Yeah, this all just whoop, down to the identity matrix and just gives you straight up a formula for A. A is in fact equal to E1 inverse, E2 inverse, right? Dot 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 EK inverse. Ah, I think inadvertently in the middle of this proof we've discovered another corollary, right? Corollary. If AX equals to 0, if and only if x equals to 0, then A is a product of elementary matrices. Not as useful a corollary as the one above it, but nevertheless interesting, right? You see how that goes? We just assumed AX equal to 0 only if x equal to 0. We did this calculation. We found this formula. A is a product of these guys. But remember, the inverse of any elementary matrix is itself an elementary matrix. All right, great. Now what? Now, we'd like to show that we still haven't done this yet, right? We need to come back here and prove that this is also true. So then how does that go? Well, we take this formula, right? Let me call it Pac-Man. And let Pac-Man eat this equation here, right? And so what's that go like? What's that look like? That looks like E1, E1 inverse, E2 inverse, dot, 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 EK inverse times what? That's A, right? This is A. And then E, what was E? You guys you made me define it. That's EK, dot, 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 E2, E1, all right? And how does this simplify? Again, the same truncation, right? The inverse of the matrix gives the identity matrix, identity matrix, identity matrix. We just keep, it collapses down into one big old elementary matrix. And so that's what we wanted. Right, so we verified that this equation is true. In other words, we've shown that both AB is equal to I and BA is equal to I, right? So in other words, this E, long story short, to summarize, A inverse is actually equal to the E that we discovered earlier in this argument, right? There's another yeah, go ahead.
Right at the beginning of this, the AX equals 0. What exactly is that saying?
It's saying that there's a square matrix that only has 0 as its homogeneous solution if we treat the matrix as a coefficient matrix of a system. So this is n equations and n unknowns. For that n equations and n unknowns, we only have the 0 solution. If you want me to write it out in gory detail, it's like A11x1 plus A12x2 plus dot 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 A1n xn. And then there's n of those going all the way down to AN1x1 plus AN2x2 plus A dot 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 ANN xn. Those equals 0, 0, stack of zeros. N equations, n unknowns. It's saying for that n, for the system, which has A as its coefficient matrix, we only get the 0 solution. That's what that first line says. In other words, the homogeneous equation, AX equal to 0, only has the 0 solution. There's yet another corollary to see here. And this one's actually super useful because it halves our work. Check this out. Think about this. Another thing you can see from this calculation, corollary, for A in R n by n, if AB is equal to I, then BA is equal to I. In other words, we only actually need to check, and vice versa. If AB is equal, if BA is equal to I, then AB is equal to I. So the definition I gave, it required both, right? And yet it turns out, if you have one, you automatically have the other. Do you guys ever found the inverse of anything else? How about pre-calculus? Right? You guys remember pre-calculus, right? We invert functions there. Does it have to go both ways? Like if you just a reminder. There we go. Just a reminder. So, how's this go? Definition, if you have f is a function from like a to b, then f inverse has to be a function from b to a, right? And you have to have the following, right? F of f inverse of y is equal to y for all y in b, and f inverse of f of x has to be equal to x for all x in a. So another way of looking at this is that f composed with f inverse has to be equal to the identity function on b, and f inverse composed with f has to be the identity function on a. So the identity function, what's the identity function? That's kind of the right idea, but more, yeah. F of x equals x, right? So like the identity on a, for instance, of x is equal to x for all x in a. That's the definition of the identity function on a. It's a very boring function. It just spits right back out what you give it. So this is the definition of inverse of a function, all right? So it has to have both composition rules. It has to have f composed with f inverse as the identity, and f inverse composed with f as the identity. And for functions, it is not enough. It is not enough to just check one of these or the other. You can have one of these work and the other fall down. This is possible. However, for matrix inversion, we're very fortunate. It's much more special. If basically one of these holds, the other automatically holds. That's essentially what this corollary is saying. If you have a left inverse, you automatically have a right inverse and vice versa. That's super nice because now that we're past this unpleasantry, we can just use it, right? Any questions before I go on here? All right, so proposition. Actually, this is pretty much a corollary, but I called it a proposition in the notes. If A inverse exists, then A inverse is unique. So like there's a unique inverse for an invertible matrix, right? And how would you establish the truth of something like that? If A inverse exists, what's that mean? So suppose that A inverse is two things, right? Like B, and suppose A inverse was also equal to C, right? What would that mean? That would mean on the one hand, BA was equal to I, right? And also what? Like CA was equal to I, right? But not just that, right? We also have AB is equal to I and AC is equal to I, right? How could you use these equations to show that B is equal to C? Well, let's see here. What I would do is maybe take this one. I mean, it doesn't matter. There's lots of ways to go. I take this equation, I multiply by C on the left. So CAB is equal to CI, right? Do you guys follow that? But then what is CA equal to? Right. See, this right here is I. So we've got I times B is equal to C times I, also known as B equals C. All right, so there you go. If the inverse exists, It has to be unique. All right. Now, to help you with the homework problem, let me go over something I share with all my calculus. If you've had a calculus class with me, you've already seen this. But there is a wonderful formula for the 2 by 2 matrix. If you've got a matrix A, B, C, D, all right, and you want to talk about the inverse of that, it is equal to 1 over AD minus BC times D minus B minus CA, provided what? This quantity AD minus BC is not equal to 0, right? Now, I haven't motivated that, all right? I actually will show you a derivation of this formula later in the course, right? In fact, this can be derived from something called Cramer's rule, and along with it, a formula, a general formula for the inverse of any n by n matrix. You're like, wait a minute, there's just a formula? Why don't you just teach it to us? It's because the formula beyond the 2 by 2 matrix is onerous. It's nefarious. It is unsettling if you see a student memorize it. And it's the wrong way to calculate. There's a better way, which we'll soon discover here today, together, soon. But for now, how would you check that this is true? All you got to do is what? To check that the inverse of a matrix is actually the inverse, I'm not going to actually do this, but I'll just say the proof is this. Multiply A, B, C, D, right, times this formula. So there's a scalar, right? D minus B minus C, A. And if you work through it, what you're going to get is 1 over AD minus BC. And then this matrix multiplication works out to AD minus BC, 0, 0, and AD minus BC, which of course is 1, 0, 0, 1, which shows you, yay, it's the inverse. All right, so we can calculate the inverse of any 2 by 2 matrix. That's pretty cool. Application. Should do at least one of these. So how about this? If you got the matrix cosine theta, sine theta, minus sine theta, cosine theta, let's say, and you want to find the inverse of that matrix, can you? What do you think? All right, so my A and D are equal. So we flip A and D. It doesn't look like anything happened, right? And let's see, my AD minus BC is cosine squared theta minus a minus sine theta times minus, anyway, it's plus sine squared theta. So I flip cosine to itself, which is kind of a non-event. And we put minuses on the off diagonals. So I get minus sine theta, and minus a minus sine theta is sine theta. So what's that? Cosine theta minus sine theta, cosine theta. Hey, apparently we can always invert this matrix, right? This 2 by 2 matrix is always invertible. Can you guys explain to me the meaning of this? How about this? I could write this as cosine of minus theta, sine of minus theta, minus the sine of minus theta, cosine of minus theta. So what's going on here? The original matrix, if we study how it multiplies a vector in the plane, what you'll find is it rotates by angle theta. The inverse of the matrix rotates by angle. See, if this matrix rotates by angle theta, what angle does this matrix rotate by? Minus theta. So rotate by theta, rotate by minus theta. Those are inverse. Makes sense. I'm being a little bit cagey here. I haven't said the words clockwise or counterclockwise because I'm not sure. You'd have to work it out, okay? But that would be easy enough to do by just, putting in a vector and seeing what happens for a given choice of theta. All right, let's go on here. So we have another theorem. And the theorem says this: if you have A and B invertible in Rn by n are invertible, all right, and you got Z and W in Rn by m, all right, and C, an element of R, is, well, has C not equal to 0, all right, then what? You have a few properties. Here's some properties. The product of AB inverse, the inverse of the product of AB is actually B inverse A inverse. Number 2, C times A inverse is, now here's a place you'll see a fraction. 1 over C, honest to goodness fraction right there, times A inverse. All right. Number 3, XA equal to Y A. Where's X and Y coming from? Oh, my bad. I see what I did. My eyes skipped over this bit. So X and Y were where? For this to make sense, A is what? N by M? N by N? Like nanu nanu cross nanu nanu. So X must be M by N. M by N. All right. Like that. Then that implies what? For AZ equals to AW implies what? So what, I mean, the proof here is just a calculation, right? How do you solve this? How do you get rid of A? What do you do? Multiply both sides on the right by what? By A inverse, right? That gives you xi equals to yi, therefore x equals to y. Az equal to aw multiplied by A inverse on the left. And then you get z equals to iw, which gives you z equals to w, right? Yeah.
What are the bars like above and below the x and y mean? Or is that just for clarity?
Oh, that's just how I draw big X and big Y.
Okay.
Yeah. I like to draw big X and big Y when I'm thinking about like a matrix. I usually, if my little x is almost always like a column vector in here. That's not like written in stone, but if I don't say otherwise, it's probably a column vector. In your homework, there's a problem. I have AV equals to B and AW equals to B. I should clarify. I think I was about to make an announcement about this last night, and I think I might have fallen asleep before I did. So V and W are assumed to be vectors in that problem, all right? And yeah. So my hint for that problem, the problem with the AV equals to B and AW equals to B, is you should think about x equals to V minus W for that problem. You should think about x equals to V minus W. Because if you do, you can show AX is equal to 0. And if AX is equal to 0, and x is not equal to 0, that means there's a linear combination of columns of A which is equal to 0. That linear combination being formed with coefficients which are not all 0, which proves that the columns are linearly dependent. I'm sorry, I think that's the solution to your homework problem. But so there's this. Now, how would we prove that like AB inverse is equal to B inverse A inverse? How would you prove that? What does it take to prove it? Because of what we've already done today, all I need to do is check out AB times what? Times B inverse A inverse. What do we get? B times B inverse is what? I but then I times A is A again, so I get A times A inverse, which then is equal to I, right? So that means that the matrix B inverse A inverse is 1, for which when I multiply on the right of AB, I get I. Therefore, by like the third corollary I stated on the left board, this proves that AB inverse is indeed B inverse A inverse. Yay! Right? And the proof of 2 is very similar. All you need to do is just, multiply CA by 1 over C A inverse. Properties of matrix multiplication say that's C times 1 over C out front, and then you've got A times A inverse, which, by the way, is the number 1 times the identity matrix, which is the identity matrix, which then implies that CA inverse is indeed the reciprocal of C times the multiplicative inverse of A. I don't prove too much in here, but I do need to prove some things here and there. This is one of those days. All right. Great. So these are the basic things we know about invertible matrices. Can you say more? I think we can glean a little bit more from what we've done today. Let's get it over with. Another theorem we can notice here. AX equals to 0 if and only if x equals to 0 is really saying what? This is the same as what? That's the same as like x1 column 1 of A plus x2 column 2 of A plus plus xn column n of A. So here I'm talking about an n by n matrix, okay? Equals to 0 if and only if x equals to 0. So what does that mean in terms of what we talked about last class? What does it mean if a linear combination of the columns of A being equal to 0 forces the coefficients of that linear combination to all be 0? What did we say that makes the set of columns? What property do they have? Linear independence, right. So this is tantamount to saying the set column, 1 of A, column n of A are linearly independent. So another characterization of the invertibility of a matrix is that its columns are linearly independent. And you have to have the same number of columns as rows, otherwise we can't even entertain the question of inversion. Inversion is a question for square matrices. There's something called a pseudo-inverse for rectangular matrices, but that comes much later in the course. Maybe not at all. Okay, so great. Then the question is, well, this is all lovely, but how do you actually calculate the inverse of a matrix if it's not a 2 by 2, right? By the way, I had a student memorize the formula for the 3 by 3 once upon a time, but it's so hideous. I won't even share it with you. It might be in my notes, but I share my notes with you. Wait a minute. But I told the student, in no uncertain terms, do not memorize this formula. And then I'm grading his test. It's like he just like an independent study of linear algebra over the summer. It's like 2012. His name was Min. And I'm looking at Min's test that he's done, and he's got this formula for the 3 by 3 inverse, and it's like he's not shown any calculation. He's just written the formula for the inverse of a 3 by 3 matrix down. And I'm like, what's this? By what manner of magic is this? And then I realized Min has memorized my 3 by 3 inverse formula, because that's who Min is. Like, I tell him not to do something, what's he do? He does it. This is the same Min I was writing a paper with once, and it was over break, and the paper was due like December 31st. I'm sitting in Min's apartment helping with it, because my LaTeX on my machine at that point was broken, and he had some working machine where LaTeX was still working. And so I'm sitting there typing up this paper for this conference thing we'd done. And in the meanwhile, Min is sitting there. And is he helping me? Is he sitting quietly? No. For some reason, Ming has a bell. Like you'd see at a hotel, an old-timey hotel where you ring for service. And Min is sitting beside me, just hitting the bell. Ding, 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 ding. I don't know why. This is Min. So don't be like Min. Actually, if you were like Min, that wouldn't be bad. He has a postdoc at Washington, St. Louis now, and he's studying really interesting math. But anyway. So how to calculate the inverse? Let's state the problem. So how to calculate? Let me write out the problem. So what we're looking at, the problem is to find A times A inverse equals to the identity matrix, right? What is this problem, though? Let's think about this problem a little bit more in a different notation. So what we're really looking for is A times V1, V2, Vn equal to what? I. What's the identity matrix? The identity matrix, notice, is E1, E2, En. So if you look at this equation, you can do the column by column rule, seeing what this really is AV1, AV2, Avn equal to E1, E2, En. The only way these two matrices can be equal is if every single column matches. So you see, what we have to actually solve is AVI equals to EI for I equals to 1, 2, n, right? In other words, we have to solve n equations in n unknowns. How many of these, though? N of them. How do you solve a bunch of systems of equations which all share the same coefficient matrix? What do? What's the smart way to do it? Is to solve the row reduction for the super augmented matrix, right? So we can solve, let me just list them. So like we're solving AV1 equals to E1, AV2 equals to E2. Every one of these things I'm writing is n equations and n unknowns, right? So how do we solve this? We have a method that we've talked about before, right? You can just look at what's the reduced row echelon form of A concatenated not with just, so the E's are the B's. B1 is E1, then E2, right? En, right? And if it works, what you're going to get is the identity matrix, right? And then the V1, V2, Vn. If it actually has a solution. If these have solutions, right? The solution is, the solution is V1. So if I row reduce A augmented with, so let me put it in more specifically. So what you do is you calculate the reduced row echelon form of A concatenated with the identity matrix, and that will work out to A inverse, the other way around, the identity matrix with A inverse like that. Or if you calculate RREF of A with I, and it's not equal to the identity matrix with stuff, right? Then A inverse does not exist. What would it mean if it's not equal to the identity matrix with stuff? Context here. We're talking about n rows, right? So if you don't have the identity matrix in the row reduction here for the first part of it, that would mean there's a pivot column in the last half of the matrix, right? And what that would mean is that there's a linear dependence amongst the columns of A, right? The only way columns of A can be linearly independent is in fact if the row reduction of A is the identity matrix. To say otherwise is to say that there's a non-pivot column in the columns of A, which can be written as a linear combination of the pivots, hence making the columns linearly dependent, which means they wouldn't be linearly independent, but we know they must be linearly independent if the matrix is invertible. And that is the way to calculate the inverse of a matrix. Now, you're like, okay, well, we've got 4 minutes left. Show me one. I happen to have 2 that I prepared for us today. One works and one does not work. All right, so we'll look at these guys here together. if I can find them. All right, first of all, the one which does not work. Do I have my laser? I've got my lasers. All is well in the world. All right, so let me make it bigger here. So here I'm doing my matrix A, right, is that. And I have slapped the identity matrix, the 3 by 3 identity matrix next to it, all right? You guys see that? Are we good so far? So then what? So the question then is, let me write down here below the board. We're trying to calculate the inverse of what? If you believe the derivation I just went through here with you. And if you don't, you should work it out for yourself. You should convince yourself that this, this technique we're using is in fact legitimate. I hope I've told you enough to make sense of it. You know, this was not really explained in my course. It was just told to me like, this is what you do, right? But that's not how I teach, usually. So what's the inverse of that matrix? Well, you row reduce this super augmented matrix. A few steps later, we get, the row reduction gets to this. What's this mean? This means that, what this means is that the third column is actually the first two columns added together. That means there's a linear dependence amongst the columns A, which means A is not invertible. You see it? It's kind of obvious now that I say it. This first plus the second column is the third. See it? They're not linearly independent. Does not exist. On the other hand, if we look at my other example here, and I'll post both of these in the, the Canvas once I get a second. Here, we're trying to invert 618 minus 8, 511, 755. Does its inverse exist? Well, it would sure be boring if it didn't. After some row operations and some pain, it row reduces to the identity matrix and this. So the inverse is apparently 0, 5/18, minus 1/18, 1/9, minus 43 over 81, 23 over 81, minus 1/9, 23 over 162, and minus 1 over 162. Now this is a terribly useful, once you've calculated this, it's super nice because then you can solve systems with the coefficient matrix of A by just multiplication by that matrix. We'll talk more about that like next class, but anyway, that's the method to calculate inverses. So you're free to use that in the homework for this due Friday if you want, all right? But I do think you can solve all the homework this due Friday without using what we did today, but if you do use what we did today, I'm cool with it. Anyway, thanks guys.